And in the wave sound section, for the first part, your speed is 5 meters per second and your wavelength is 20. And we're using the equation v equals f lambda. Remember that the frequency, once you solve that, that is in hertz, or how many waves per second. And so to get the period, you take 1 over the frequency, and that will give you the seconds per wave. For the second one, if you're in the same spot in the ocean, the key is that the velocity is the same. So that would be 5 meters per second still from up above, same medium, same velocity. And you can use v equals f lambda again to find the new wavelength with that speed. For number 12, the velocity of our sound wave depends on the temperature of air. So we're doing 331 meters per second plus 0.6 meters per second times each degree Celsius above that. Once you have the speed, you can do v equals f times lambda to find the wavelength. And for part C, you know they're a distance of 184 meters away, so this is kind of a conversion. I found that the wavelength was 1.1 meter. So 1.1 meters is equal to 1 wavelength. And you can then convert to get how many wavelengths we're talking about. For part D, you're just using the old school velocity equation, v equals d over t. And the distance was 184 meters. And the speed you know from above. For number 13, you need to first find the speed of sound using 331 plus 0.6 times t. And then since it's a closed tube, we're using Fn equals nv over 4L. 4L. And the n represents the harmonic. For the fundamental, we're using n equals 1. For the first two overtones, since it's a closed tube, remember that resonates with the odd overtones. So we'd use n equals 3 and n equals 5. For 14, it is a string, so Fn equals nv over 2L instead. And for that, for the fundamental, we'd use n equals 1. And for the overtones, now we can use n equals 2 and n equals 3. For the light section, you do need to remember that all electromagnetic waves travel at a speed of 3 times 10 to the 8th, and that v equals f lambda still applies, so you can solve that then for the wavelength. For number 16, it's using Snell's law, n1 sine theta 1 equals n2 sine theta 2. And you need to remember that you keep your mediums and your angles together. So the index of refraction of air is 1. That's something we expect you to know and memorize. So I do 1 times sine 65 equals the index of refraction of the ocean water, which is 1.36, times sine theta 2. And to solve for the angle, remember you always have to take the inverse of a trig function, so it would be the inverse sine of the number that you get for the other side. For 17, we're looking at total internal reflection and solving for a critical angle, where the critical angle is equal to n2 divided by n1. So as it's going from diamond 2.42 into pool water 1.30, you could solve for the critical angle, and you'd have to again use the inverse sign to get an angle. For number 18, we're just doing n equals c over v. You've got the n value, you should remember what c is, and divide by the v. Moving on to optics. A photocopy machine uses lenses to reproduce images. Here you have a focal length of 12, or 0.12 meters, and the object distance is 0.24 meters. So we can use the equation 1 over f equals 1 over do plus 1 over die. and solve that for our image distance. Make sure you're remembering to take the reciprocal when solving for di. To get the magnification then, we can use negative di over dou to solve for magnification, and that can also then equal the high over ho. And we could use that to find the image height of the 0.4 centimeter print. 0.4 centimeter would be 0.004 meters. The ray diagram, this has a positive focal length, it's a lens, so we're looking at a convex lens, and the object is outside the focal point, so it'd be something like you're going in parallel, you're going down through the focus, you're going through the focus, you're refracting out parallel. Here would be your image, and it would be on the other side. It is about the same size or smaller. It's inverted, and it's real because these light rays actually meet up there. Then on the back, still using 1 over f equals 1 over dou plus 1 over di. To find the height of the image, we can do high over ho equals negative di over dou, which is our magnification equation. And the ray diagram for this one, it is a mirror with a negative focal length, so that would be a convex mirror. So remember, you go in parallel, it's reflected up from the focus, and when you go in towards the focal point, it's reflected out parallel. Those two are never going to converge, so we trace back behind the mirror and we get a smaller, erect, virtual image that's on the other side of the mirror. Continuing for these, we're the same thing, in parallel, reflected down through the focus. When you're in front of the focal point, up from the focal point, reflected out parallel, trace back. This one you'd get a larger, erect, virtual image. For number 22, you go in parallel, it will be refracted through the focal point. Go through the focal point, it's refracted out parallel. And where they cross, that would be our real image. For the last one then, you go in parallel, refracted out from the focal point. Remember, you have to use the focal point on the other side because this has a negative focal point, being a diverging lens. When you go in towards the focal point, it's refracted out parallel, and where they appear to meet would be your image, and that would be smaller, virtual, and direct.